I'm a mathematician, and so a pure mathematician, and I have 5 slides and 5 minutes to tell you something about my research in pure mathematics, which I... okay, sorry. Which I think is a pretty tough ask, so let's hope for the best. Okay, so the story I'm going to tell you is about the four-colour theorem, and as you'll discover, the real four-colour theorem is a pun, but you'll understand that later. The story started 160 years ago. A letter in a London literary magazine, you probably wouldn't find such a letter these days. Someone called FG said, in tinting maps, that means colouring a map, it's desirable to use few colours so that the countries of the map, the ones that share a border, are coloured differently so that you can actually tell them apart. FG's widely viewed to be Francis Guthrie, this person here, and apparently he was tinting a map of the counties of England when he noticed that he only needed 4 colours. Now, if you only have 3 colours, it's easy to find some maps that you can't do so that countries that are next to each other are all distinct. If you have 5 colours, then with a bit of work you can show that you can always do it, regardless of how complicated or messy the map is. But Guthrie said, I think I can do it in 4 colours no matter what map you give me. Why can no one prove this? Well, that became known as the 4-colour conjecture, and that led to 150 years worth of research. Okay. Is it important? Does it matter whether you can actually use 4 colours to colour a map? Well, no, of course not. That's not important. But what it means is that we're missing some tools, some mathematical tools to describe simple aspects of reality, and that's what drives mathematicians on. And so that became a sort of challenge problem for the 20th century. Consumed dozens of academic careers. Many, many people spent their entire career working on it. Even though those academic careers didn't resolve in a solution, well, except for one, then it still drove the development of the field that's now called graph theory, which is incredibly important in the study of networks, which I'm sure you all know are important. And it really entered the popular consciousness. Everyone knew at that time the 4-colour problem. When it was solved in 1976, it was front page news on the New York Times, and not many mathematical problems make it like that. The solvers were Harkin and Apple, who are shown there in the picture on the left in the 70s, working on a computer. Apple died a few months ago. And when this says 4 colours suffice, and that's the postage stamp imprint that their university used for the next 20 years after they'd solved it. Their proof was very controversial because it used a huge amount of computation, and it was very controversial, and some people, they would give research talks. They went to give a research talk at some university and were forbidden to speak to the graduate students in case they corrupted them with this newfangled computer stuff. But I'm not going to talk about that. I'm going to talk about a failed attempt to prove the 4-colour theorem. And I know that every equation halves your audience, but I couldn't get away with it without any. So this is Birkhoff. He decided to solve a more difficult problem. The 4-colour theorem says there is a colouring of any map that uses 4 colours. Sometimes in mathematics, it's useful to actually try to solve a harder problem than the one you're set out to. And he said, in 1912, I'm going to try and count the number of colourings of each map. And if I can prove something about that count and just show that it's positive, non-zero, then I've shown that there is at least one. And so he introduced these things which are called chromatic polynomials. Now, every map has associated with it a polynomial that counts the number of colourings. So x is a variable. If I put x equal to 4 in this horrible polynomial equation, out will pop the number 240. And if you're bored, you can work out that this has 240 different ways to color all the countries. So, his idea was, let's use, instead of using the tools of combinatorics, let's use the tools of analysis, the study of functions and where they are zero and where they're non-zero, to try and solve the four-color problem. Okay, it failed. He couldn't solve the four-color theorem like that. But the point here is, every map has one polynomial associated with it that counts the number of colorings. What they did show, Birkhoff and Lewis showed, is that this polynomial, which should be positive when you put x equals 4, they managed to show that it was positive whenever x was 5 or any number, integer, which is a number of colors, or a real number, 5.273, 6.417, blah, blah, blah. It makes no sense to talk about coloring a graph with 5.273 colors, but you can take his polynomial, you can put x equals 5.273, and you'll get a number. So, I've drawn a number line here. I draw those lots for my kids. And I've drawn a little green bit there to show that there are no values there where p of x is equal to 0. That's what that shows. P of x is always positive if you put x in any of those places. So their question was, for which real numbers can you find a map where this polynomial is equal to 0? If you could show that that set of real numbers did not contain 4, then you would show that every map has a 4 coloring. So, they proved this, but they conjectured this, which I like to call the real 4-color conjecture, because it's like the 4-color conjecture but with real numbers instead of with integers. What they conjectured is that, in fact, this polynomial, every map, its polynomial, put any number from 4 upwards into the polynomial, and you'll get a positive number. So they conjectured that this area here, if you put x to be one of those values, then the polynomial is not 0. Okay. Well, what's known about that? What's known? Well, I proved a few years ago that you can take x as close as you want to 4, but sadly less than 4, and you can find a map where the polynomial is equal to 0. So still, we're stuck with this area of uncertainty. The very first question that they ever said is still unsolved 60, 70 years later. Alan Sokal proved that all complex values, now sorry for those who don't know what a complex number is, it's like a real number but more complicated. Actually, you can find maps where that's 0 arbitrarily close to any number. Alan Sokal's a collaborator and friend of mine, and you may know him because he's actually famous for a very famous hoax on a postmodernist magazine. But he's also a brilliant statistical physicist. So you may say, well, why on earth is a brilliant statistical physicist interested in working out whether maps have 4.2 colorings? In fact, you may answer, does this really matter to anyone at all? Well, in one sense the answer is no, it doesn't matter whether there are any of these things between 4 and 5. But pure mathematicians follow things just for curiosity. And what's astonishing is how often, where a pure mathematician goes from curiosity, somehow, for some obscure reason, the universe follows. And in fact, the chromatic polynomial of a graph is actually, well, I've written it down here, it doesn't mean anything more to me than it does to you, the zero temperature limit of the partition function of the anti-ferromagnetic Q-state Potts model. Potts is a statistical physicist from Adelaide, he died a few years ago. And what's astonishing is that Statistical physicists study when materials exhibit phase transitions, when something suddenly becomes magnetic. Those things depend, believe it or not, on the complex zeros of these functions. And so, chromatic polynomials are graphs. Statistical physicists for 60 years have both